On Friday, we talked about cell voltage, how we calculate the cell voltage. The equation, we want to know how much the cell goes. We take the half reaction, or the half cell potential minus the half cell potential. Now, is it anode minus cathode or cathode minus anode? Yes? Cathode minus anode. Now, this equation comes from a process similar to what we did earlier in thermochemistry, where we flipped the reaction, multiplied it to get the electrons, etc. Now, the difference here, why we don't do that process where we flip and multiply, is remember that voltage is the electric potential is the energy per unit charge. So if I multiply an equation by 3, I've multiplied the energy by 3, but I've also multiplied the per unit charge by 3. So our cell potentials don't change. And that's why we're able to do it this way. Where in thermochemistry, we're talking about energy straight across and not energy per unit charge. So we just multiplied the energy. So we have the question here. During a lab experiment, the teacher gives the students an unknown metal that is silver in color and a 0.1 or 1.0 mole per liter solution. The lab is to determine the identity of the metal. One student decides to use electrochemistry to help him determine the identity of the metal. He creates a standard half cell with the unknown metal and connects it to a copper half cell. So basically, he does this. This is copper. Oak Ridge, my real drawing. And this is the unknown. He also connects it to a voltmeter. Okay. This is what he records for the evidence. The voltmeter reads 0.76. The blue color of the copper solution decreases in intensity. And the copper gains mass as the cell operates. Now, the voltmeter reading is nice. We're going to plug that in. Where are we going to plug that in here? Yes? Anybody? Is it going to go the cathode, the anode, or the total overall? Yes? It's the total. We're going to put 0.76 here. Now we know copper, or we can find copper. Copper has a 0.34 volt, positive 0.3 volt half cell potential. And that's from your data book. But we don't know if I put it under the cathode one or the anode one right now. That's where we're going to use these two pieces of information at the bottom. Okay. These two things tell me what? You have this guy gaining mass, and you have the blue color decreasing in intensity. Get out of this. No, I'm not. This is our half cell reaction. The copper is increasing in intensity, and the copper is gaining mass, and the blue color is decreasing in intensity. Is the reaction going in this direction, or is it flipped? I'm gaining copper, and I'm losing copper 2 plus. So this is the reaction that is taking place. Is that the cathode half reaction or the anode half reaction going in this direction. This is your cathode half reaction. So basically what those two pieces of information at the bottom tells you is that my copper is my cathode. So these three pieces of information tell you that the copper is the cathode. And again, they all tell you that your copper 2+ is gaining electrons to become copper solid. Another piece of information that wasn't given there, the unknown metal loses mass as it operates. So that means that the unknown metal is going the other direction. Whatever that unknown metal is, I'll just call it A. It is losing mass. Now, I have no idea if this is the reaction or not, but it gives you an idea of what's happening. That tells you we have the unknown. So the empirical properties allowed to figure out which one was the cathode, which was the anode. And therefore, now we can plug in what we know. So, if I'm correct, it is 0.76, right? So, we just plug everything in we know. 0.76 minus 0.34 is equal to the negative cell potential at the anode. So we have 0.42 negative 0.42 volts is our cell potential, or half cell potential at the anode. I'm going to open up my data book on screen. So we have nothing that's exactly negative 0.42. We have a grouping like this that's close. Okay? So according to our potential, or according to our electrical potential, we have either this one, this one, this one, or that one are our possible reaction, our possible anodes. We could either have the selenium with hydrogen ion, we could have the cadmium half cell, the chromium 2, chromium 3 half cell, or the iron 2 iron cell. Of those 5 options, which are the only 2 that make sense? Yes? Well, I'll agree with the iron, not so much the selenium. Because selenium is a solid, but selenium is not a metal, right? Selenium is on our right side of our table. So selenium is a non-metal. So yes, it's a solid, but it's a non-metal, so it doesn't have the same principles as metal. The 2 that are here is this one and that one. Those are the possibilities. Because they contain, that half reaction has a metal. And we were given a silvery metal. Okay? So we have 2 choices here. The other ones, the chromium 3, chromium 2, well, there's no metal in that reaction. That's just an ion thing. And we know that the metal was involved in the reaction because it lost mass. So our possibilities are not chromium, it was cadmium, wasn't it? I actually don't remember what it was. It was cadmium or iron. And the reasoning for that because they have been close. One is 0.40, one is negative 0.40, one is negative 0.45. Yeah, the cadmium is just a bit closer, but I wouldn't want to make any guesses on that from there. Now, the question that we could ask now, what reaction would you be able to use to distinguish between them? So we have 2 possibilities, right? Which reaction do we want to deal with, or what reaction could I use to figure out between them? The chromium 3 plus and the chromium 2 plus is right between. Okay. So what you would have is, if I hook this cell up to that cell, the chromium 3 plus, or the electrode in the chromium 3 plus solution, chromium 3 plus / chromium 2 plus solution, would be the cathode. So electrons would flow towards the cathode. And you could use a voltmeter to figure out that they are flowing towards the cathode. If I hooked it up to the cadmium half cell, well, you got OA, RA, OA, RA. Well, that's our strongest OA. You would have electrons flowing towards the cadmium electrode. because that one would act as your cathode. So we could, that next step in the problem is, okay, how do I distinguish? I go make a chromium 3 plus, chromium 2 plus half cell and figure out which way the electrons run. Now, there is a bit of a problem with that, is they're essentially the same electrical cell potential. So really, the cadmium 2 plus is not much greater of a OA than the chromium 3 plus. So we would, if I was to do a question like that, they'd be much farther apart in terms of cell potential. Any questions on that one? Okay, I did put the cadmium. I should have put the iron in here. So your homework, well, what you're going to have for the rest of the day, this period, and however much of the next period that you use, correct, or enough of it, you're going to do questions on page 631, 11 through 16. And then on that assignment, you're going to do questions 1 and 3 and 5. 1, 3, and 5. We will, when we start to talk about both electrolytic cells, I'll get you to do 2 and 4. Okay. Any questions for today? Yeah. Yes, you can go to your textbook. I have a question. How many times a week do I use my textbook? I don't know. Somewhere between 3 and 4. Do the homework questions first, then do the assignment.